Let's study now torque experienced by an electric dipole in a uniform electric field. So let's take a uniform electric field. Uniform electric field means all the electric field lines are parallel to each other. Okay. Alright. Okay. Now let's see this thing. So now let me draw the electric field lines. So this is the electric field here. Lines here. Let this electric field be E vector. Okay. Now let me take a dipole. A dipole, you remember, it is having two charges here, a positive charge, that is plus q, and a negative charge, that is minus q. It's a negative charge here, that is minus q, and it has a distance here, that is 2a. Okay, so let me draw the distance here. Okay, so let this be the midpoint of the dipole. The midpoint we write as O. This distance is a. This distance also is a. Now you see the dipole has a positive charge now. So and the electric field starts from positive to negative. So positive and positive will repel each other. So this side will have a force like this way. Okay. And let us see what this force will be. Okay. For that, let's take the formula for electric field. We know electric field formula E is equal to F by Q. You cross multiply and rearrange, we get F is equal to QE. So the force on this side will be Q times E. This is the force here. Okay. Now let's see the force on down. So below that you can see the minus Q now. So this side, this thing will go towards the left side because there's a positive charge here, it will be attracted. Okay. So let's see what is the force here in this case. So again formula F is equal to QE, so I'll use that. So we have F is equal to, here we have minus Q, so we get here minus Q times E. So the force will be minus QE. Okay, so you can see one force goes this side and the force goes this side, so it will make the dipole to rotate. Okay, so as the dipole rotates, it experiences a torque. Okay, we are going to find what is the torque here. Now let us see this distance here. Let me draw a triangle like this way. Okay, now if you notice that there's an angle here, that is theta. Okay, let me draw this triangle outside. So I've drawn it here. Now you see the distance is A and A, that is 2A. This is 2A. The angle is theta. Now our aim is to find what is this distance here. Okay, so for that I'll use sine theta. Remember, sine theta is opposite side by hypotenuse. Okay, so in this case we get sine theta is equal to, opposite side we leave it as it is, hypotenuse is what, that is 2a. So 2a, when you cross multiply we get this opposite side equal to be, right, this side we get opposite side is equal to 2a into sine theta. Okay, now so this distance will be 2a sine theta. That's how we get this in the book. Okay, now let's see an expression for the torque. So torque formula is, torque, that is given tau is equal to distance cross F. This is all vectors. So torque is equal to distance vector cross the effect. It's a cross product. Okay, now let me take this portion here, this portion first below. So on this portion, let us see here what will be the torque here. So torque is the distance cross force now. So distance is what, R. Okay, now this distance O, I'll name this part as A. So this is O, A, and this is B. Now OA, so distance is OA vector, it's actually vector here, and then cross force, here the force down will be minus QE, so Q times E. Electric field is a vector quantity. Okay, then again you notice that there's a force on top also, there's a force here, so we must take this into some account, or there's a torque also, so you have to add the torque, so that's plus, for this distance will be OB. Okay, so let me write this OB cross, and then you see that will be Q times E because the force is QE. Now let us see what is the formula for cross product. Okay, I'll write this side. A vector cross B vector is equal to AB sine theta. Now this is actually magnitude of A, magnitude of B, so I can write this way: magnitude of A times magnitude of B into sine theta. Okay, let me use this formula here now. Okay, I'm going to use it here. So OA, instead of writing OA, you can write here as magnitude of OA vector, I'm using this formula here, into magnitude of QE vector, then sine theta, plus OB. Again, this is a vector here, OB is a vector quantity. So right here, this form, using this formula, AB sine theta, magnitude of OB vector into magnitude of QE vector, Q is a vector here, into sine theta. Now what is OA means? Okay, OA means it is value is A. Okay, so let me write it here. OA is A, and then you take magnitude, means the minus sign will go away. So get here OA, that's A into Q into E sine theta, plus OB, the value of OB is also A only. Okay, see this distance here, that is A. Then again QE sine theta. Now you see that this is same only, so you can write two times, it's just add them. So it will get here 2QA E sine theta. But we know that the dipole moment, that is 2QA, is the dipole moment. So right here we know that the formula, that is P is equal to 2QA. P means dipole moment, twice of the distance, twice of the charge into the distance. Okay, or you can write charge into the distance 2A. So instead in 2QA we write as P into E sine theta. Okay, so this is the torque is PE sine theta. Now how this comes instead of vector? See, at this stage we are taking magnitudes now. So here also you write here magnitude of torque. Okay, when you take magnitude, we just take only the numbers, we don't take this as a vector. Now we got this torque is PE sine theta. This is a very important formula for the torque. Okay, we'll be using this as sums there. In fact, we'll see a small sum. Now we must again write in vector form. Okay, to write again vector form, I'll take this torque here. Torque is equal, I'll use the same thing, AB sine theta is equal to A vector cross B vector. So you can write as P vector cross E vector. Okay, so this value will give us the torque of a dipole kept in a uniform electric field. Okay, now let us see what will happen if there is a non-uniform electric field. Okay, what will happen to the torque? Now I'll draw a non-uniform electric field. Okay, for example, like this way. You see, these are curvy lines. Okay, there is no straight lines here. So electric field is non-uniform. This is the electric field here, E vector. Now let us take the dipole here again. Dipole consists of a positive charge, that is Q, and plus Q, negative charge, that is minus Q. It's a negative charge here, that is minus Q. Distance is 2A, we know. So I'll draw distance also. Distance is 2A. Now what will happen? Again we know that this will go the right side. Okay, so then let's see the force here. The force will be Q into E, but you notice the electric field is not same. So you can write here the force is Q times E1, and then this side down you can notice the dipole will go this side. This force will be minus Q times E2. Why? Because the electric field is not same, it is different. So you can see at this stage for a non-uniform, this is actually non-uniform electric field. Non-uniform electric field. For non-uniform electric field, what happens? There will be a net torque there. Okay, torque means what? It causes a rotation, and then there is also net force also. Okay, and this full dipole will actually turn this side. It will travel also sometimes. Okay, so in non-uniform electric field, there is a net torque and a net force.